Number 11 is actually using the same equation as number 10, but we're being asked for a different species. Again, in number 11, we're told that the rate at a particular instant in the reaction is 2.0 times 10 to the minus 5 moles per liter per second. And we are being asked specifically for the rate of disappearance, which is like a rate of consumption, of the reactant C2H4Br2. And so you see the simple rate of change would be this, and that would be a negative value because its concentration is decreasing over time. And so if I put a negative sign in front of that, I get that rate of disappearance as a positive number. And so they're asking for this value. And so I can write that the rate of this reaction is equal to, for every species, let's just say this instead of writing it out. The reaction rate would be equal to a minus delta C2H4Br2 by delta T. It would be equal to a minus 1/3 delta Ki over delta T. It would be equal to a positive delta C2H4 over delta T, which is equal to a positive 1/2 delta Kbr over delta T, and that would be equal to a positive delta Ki3 over delta T. Well, we can see right away that the rate of disappearance, as they're calling it in number 11, of species C2H4Br2 is actually equal to the rate of the reaction because the coefficient here is 1. And so the rate is equal to minus delta C2H4Br2 over delta T. And so the negative value of delta C2H4Br2, we're just going in circles here, is equal to the rate is equal to 2.0 times 10 to the minus 5 molarity times seconds to the minus 1. So you see, as we do a few of these, as you do more of these, you'll be able to do, especially ones like this, by inspection, because the coefficient here was 1. So we knew that the rate of the reaction and the rate of change of C2H4Br2 was the same numerically. And for number 11, that's an answer of B.